Everyone. I am going to be showing you SOLIDWORKS Plastics. And like Dean had mentioned, we're going to look at the fill pack and then sample of the warp cool module. So there are three modules that Plastics comes in. It is the Pro, Premium, and Advanced. The Pro is your fill module. The Premium has fill and pack. And then the Advanced has the fill pack and then warp and cool added to it. So SOLIDWORKS Plastics is an add-in module that I'm going to set here from add-ins. Down here it is on Plastics, and I'm going to have that load in. It gives us a tab over here called the Plastics Manager, that we'll talk about in a second, plus another tab up here on the Command Manager for turning on options and getting into different aspects of the software. Leading with the left side over here where we see the mesh, first thing we have to do with any simulation is generate a mesh. There are two types, the shell and solid. Shell is for parts that have a constant wall thickness, and then solid are for parts that of course don't, like you see on here where we have a difference in thicknesses as we go through. I'm going to run this in a shell mesh, and once we have this generated, we will see much more information in that menu. So this basically kind of acts as a wizard as we step through here. These options down here have to do with cooling and the warp setup. So we're going to skip those for right now. I'm just going to hit Next. And on the next screen here in this category, if we had multiple domains or multiple solid bodies in a single part, Plastics does not work on an assembly. So we would need to build in a save that assembly out as a multi-part body to bring it to use it in here. But we can have, where we would label this as a cavity, we can also have insert, and then if we were doing warp and cool, we would have a cooling channel and mold. So it can use inserts such as if you have a brass insert or steel, or even the insert can be used as a secondary, like if you're doing a multi-shot mold where the insert would be your first shot, and then your cavity would be your second. We only have one, so we're just going to hit Next again. And now we get into our meshing module here, where we generate a mesh. And you can kind of see on the screen, I put in 50 thou. We are in English units right now, to generate across there. And the thing what I got to look at here is, does it pick up the detail that I need outside and inside? I do have some other options that are available though to me. So if I even loosen this up to, let's say, a quarter mesh, you can see it becomes really kind of jagged on the details like you see inside of here and outside the wall. It looks more like a chamfer than it does an actual fillet. We do have the ability to set an auto. So there's no local refinement. Set allows me to localize. So if I wanted to have these surfaces on this mesh right here to be a tighter value, I can set those up, and then it would use the triangle size for everything else. Or I can set auto. And auto has basically a slider down here that I can set up. And when I do that, you can see kind of based on the two values from the triangle size and this auto, it tries to put in some deviation changes where it needs to do that. So if I tighten this up even more, you can see how it gets a little tighter and tighter as far as the mesh follows. So there is a kind of a balance act that you have to do between this, because you don't want to set this so tight that you have an overabundance of mesh elements that you would not necessarily need to generate the output for the fill or pack or whatever we're doing. But you do want it tight enough that it does follow the contours of the shape. So we could even maybe loosen this up a little bit here. More. There we go. That looks pretty good. I'm going to hit Next to that. Gives us a summary, and the biggest thing is that it is waterproof. That's good. And one thing to note on this part is an imported part into SOLIDWORKS. It's not necessarily a native part, so it can work on both of those. And we're going to transform it. Transforming gives us kind of a cross-section view through. We can see the internals of the mesh and see if everything looks good, and it does in this case. And I'm going to hit OK to that. So now that it's written up its files that it needs for the mesh, you can see we have over on the right here, we're doing a solid type, elements of 28,000, and a node. So if we look at the mesh again, this is an element, the little leg you see, the line, and then a node is the connection point of all of those together. Next thing, you can see the menu has expanded a lot more because we have that mesh built. And the material, we can kind of step down here. So SOLIDWORKS Plastics has over 5,000 different material types. We can't add to the library if it's not available in here. We can also search. So if I'm looking for like a peak, you can see I just type in a keyword and it gives me the different values that I have. Also, I can go in and search by options. So if I want to have a certain fiber count or mold temp that I'm looking for, or melt, I can do that underneath also peak if I wanted to do that. So it's hard to kind of see there, but the solid has a little green check, so does the polymer. The next thing I can do is look at the fill, pack, and warp settings if that's where I want to take this to. Notice down here in the run, I do not have any cool because I skipped that section at the very beginning when I was creating the mesh. So if we just briefly look at my fill settings, I'm going to use all the defaults here and let it figure out the filling time for me also. But notice here it also has a fiber orientation calculation because the material contains 30% weight of fiber. So we will actually see that calculation put into it also. Let's go down to our injection location, and we're going to inject here at the tab front right there. And I can actually run a predicted flow pattern on that after I add it here to kind of give me an idea of what that looks like. I also have tools if I want to up to 10 gates, have it predict for me and place the gates on the part. And a lot of times it puts it in areas that you would not necessarily gate, but it gives you an idea of the region maybe that you need to have that gate added. So basically we're ready to run this first flow analysis on this. So if we start with our solid, we've got that done, we've got our polymer, we've got our fill settings, and we have our injection location. So now we can actually let this run and start looking at some results. This should run fairly quick. This does use all your cores and threads on your computer that you have. So it is using, I've got a quad core that I'm running, so it actually is running 8 threads. And this screen right here is kind of giving us a iteration view as it steps through here. So we've got iterations, we've got time in seconds, we've got pressure, temperature, and then the percentage. Now one thing it gave me was a little warning up here that we're getting very close to our max injection pressure, which is, I believe it's 100 megapascals, and I can set that, I can vary it, but by default that's what it was. And it's still trying to fill it out to that level, and we'll see if it does it or if it actually short shots. I'll let this run just a little bit more here. It's at about 58%, coming up on 60 now. It should refresh itself again. We're at 99.22 megapascals, so we're approaching our limit. But it is still calculating out. Here comes 70%. And it looks like it actually shorted out. So let's take a look at the summary here. Text file. We read down on the very bottom. Don't see it in there, but let's take a look at the results and see what we get. So yeah, the fill time, it did not go all the way to the end. So what we can do then is right here, the injection pressure limit. We can set that a little bit higher. And we can set this up too to go by machines. So if you have an Engel or a Toyo or something like that that you want to utilize as the machine, you can set that up also. Just run through here one more time and see if we can get that pressure limit to work for us a little better. Now we are running PEEK, which is a little bit more difficult material to try to pack out and fill out. Coming up here on 40%. Show the task manager here. You can see the CPUs are all of them are being used. Coming up on 60%. Warning again that we're getting close to the injection temp, or injection pressure, sorry. So we'll see if we can achieve the full fill here. See what happens. $90. And there's 100. So we made it that time with a little bit more pressure behind it. So now that we have some results, we can see when this gets completed here, a couple different things on the screen will happen. One is this results advisor on the right side, and it's at red, which means we can successfully fill it, but we're at or over 90% of the maximum injection pressure. So we're way up there, and you can see it's could cause filling, packing problems to molding machine. So maybe we need to change the temperature, maybe we need to change the material. We don't know, and that's what plastics allows us to do, is analyze that digitally before even making a prototype mold, and finding the results that aren't going to work at that level. So we can look at things, different things that we have in our flow results in this case. One is the actual flow front. And this is because we did it in solid. This is actually in 3 dimensions. And if I scroll it back and forth here, you can kind of see it'll go up and fill through that rib. And then continue on down the channel, coming around up the end. And then finally filling out the little tab at the very end of it. But there's a lot more to it that we can view also. One is our pressures. Pressure at the pack switch time that occurs, our temperatures. Now this looks like it's all blue down here in this temp, but we also have the ability to put in clipping planes, and we can actually look internally to the part and see that, of course, with a lot hotter core inside of there in certain areas than just on that outside. Again, a lot of analysis that you can do right here on screen in the digital side of things. There's bulk temp, flow front, shear stress is a very important, shear rate. Cooling time that it would take, again, you can cross-section that and look at the internal core of it. Temperature at the end of cooling that it's calculating out, even though we didn't do a cooling analysis, but this is kind of making a prediction. Sink marks. You can see where sink marks will occur on the detail. So what you see in red areas there are tooth thou that it's predicting. If we had a multi-gate, it would show us the gate filling contribution. We only have one gate, so of course everything is green. And then ease of fill is allowing us to see where the problem areas are. And it happens to be down here. So what tells me is that material is probably starting to solidify as it's trying to push and get down to this area. So that's not necessarily a good thing in that case. We can look at our velocity vectors. And let's change the length a little bit here so we can kind of see. That gives you an idea of what the velocity looks like going through there, vector lengths and their changes. And because we had fiber, we can also look at fiber orientation. We can control what those lengths look like. We can look for any weld lines. This case doesn't have any of them. And we can look for air traps. So a lot of the results we can view inside, of course, the flow results that we ran. Now, if I ran pack, we'd have flow and pack side of things. But the other thing we can do outside of the results, the actual like flow results, is an XY plot, which gives us a little bit more information of what's going on here. In that, you can look at the pressure, and you can see it's climbing pretty steadily as it goes up. We can look at the inlet flow rate, and when it gets out here to 0.13 seconds, it starts to taper off. We can look at the X, Y, and Z clamping, so that would allow us to know what our tonnage would be. And then under node pressure down here in the bottom, I can actually put in points, probe points that I want along, and have it give me information on the graph. The other thing I can do with these probe points is if I put in a reference plane, depending on which plane, so right there, I can jump in here and put in points that would be right through the cross-section of that plane. So right there I can add one. Maybe I want another one down here. And let's put one there. And then one out here, let's say. And all those points reside on that plane itself. So it's nice when you maybe have an insert and you want to view it cross-sectioning through the insert and then through the part itself. The other, that's pressure side that I'm showing. I can switch to actual temperature. And you can see where the flow front comes in as these little spikes occur right here as it ramps up on the different points across. So it gives us a lot of different ways to view the actual output information from this. The other thing we can do is actually generate a Word or PowerPoint. It's going to generate a PowerPoint of our results. Something like that. We can put an introduction if we want, special notes. Then I can tell it to generate all the image files of those results. And I'll let this, give it a second here to output everything. And I'm going to open up where the data would be. Now it's writing the actual PowerPoint, and in a second it'll tell us that it's done, and we can view it. So it's all completed. Here's the PowerPoint, and we can bring that up and review it. And you can see all of the output that it gave automatically for us, all the different graphs, all the charts that we looked at, cross sections. Fill time, here's the actual animation, and all those different image sets that I just went through and showed you. That is a template that can be customized so it fits into your business model and with your own logo and all of that type of stuff also. So that can be done very easily. The next thing is, let's talk about pack on this part. Pack settings, again, I can have it automatically, or I can put in the holding time, and temperature. One other thing also is that I can have it do a profile, and I can actually input a profile and match what I would see on a press. I can also do that on the fill side. And the other thing is residual stress calculation. An interesting thing about that is when we have that calculated, we can output that information, or the in-mold stress, when we would run a warp. We can bring that back into SOLIDWORKS simulation tools and have that as a pre-process setup in simulation, that this part already has these stresses built into it from the molding cycle. So I'm just going to let the pack side of things run here. This should run fairly quick. And then we can look at those results quick. And then I will show you an example that has the warp and cool module added into it. The nice thing with the way this runs is that if I'm not like seeing the results that I want, especially if you're running the flow, I can stop this at any time and stop the whole procedure instead of having to wait for it to get completely done. All right, so there the pack results are in. So there's the pressures at the end of pack now. We can look at the temperature, which looks different. It's a little bit cooler across in here. Still kind of warm down on the bottom here, of course, and cooling off down in the end there. We can also control these clipping planes back and forth, so we can cross-section through it. Bulk temp, shear stress, shear rate, volumetric, temperature, and so forth. So all of them, kind of similar to what the flow results were, but this was at the end of the filling only. This is at the end of pack now. So now we're into the cool stage of things. So speaking of that, let me load in the other example that I have. And let's get the other results loaded so we can look through them all. There we go. All right, so this one's set up very similar to what I just showed in the last example, except in this case, instead of just gating down here, I actually have the sprue and runner and gate system in, and I'm gating at the top of the sprue to simulate actually the whole system now of how this is going to work. So if we look at the fill time in this case, run it back and forward here, you can kind of see the way it advances through those open sections there. Kind of does a little backfill through the ribs. Again, we can certainly zoom up and analyze it a lot closer, see what's going on with everything. And then you can see how it kind of wraps itself all the way down. So looking at the pressures, temperatures, and again, just like before, we can do cross sections through it, take a look at what's going on. Look at our shear stress, shear rate. Again, we can look at the velocity vectors, fiber orientation. And in this case, we actually have some weld lines, and those appear here. From blue to green, green to red. Green to red can become basically a meld situation where it's not necessarily as strong. But what you have to do again is analyze it, view where it's at. Does it make sense that that's going to cause an issue with stress or a failure on the model? But at least it gives you that idea, and you can see it on the model. And then of course we can look at air traps, so forth. So same type of thing as we had before. We can look at the pack results quickly and do cross section. And again, you can see the temperatures. Temperature at end of pack. All the temperature, a lot of it is sitting in the core here of our sprue and runner system. And we can get into warp. Now, this is where we can actually look at the total direction, and this is everything overall. It is at a deform scale of just 1. So this is actually the way it's going to warp. The wireframe you see is the actual model, and then the actual warped model is shown in there. And we can play this and let it shrink itself and warp itself out. Now the reason it's doing it on one side versus the other has to do with our reference origin and warp reference plane, which we can set. So if I wanted that to be more in the center, I can certainly do that and have it warp that way. And it could also be warping naturally in that because of the way these ribs are exposed here versus being a lot more solid on this side. So that might be just the way it is. But you can switch that around for those different planes. Now, if it happened to be too small of a warp detection, we can also exaggerate it, which I put it at 3 times now. So you can kind of see how that side and actually this corner is curling itself up. We can look in the X value, in the Y, and in the Z directions independently or overall. We can look at the in-mold residual stress, and this is the one that I was talking about that we can actually have output then. This information from here can be saved out, brought into simulation, and used as kind of the precursor of running the simulation on it. Got quenching, and then we've got total stress without the fiber in there of this calculation. And then from the cooling side of things, this introduces in an actual cooling line that is either developed with just a simple sketch, which is the way this one is. If you look at this model, that's all that is right there, is that simple sketch that you see, sketch 49. And I declare how the diameter is, and then also the inlet and the inlet temperature, what kind of fluid is it that's going through, is a water, an oil, something like that. And then this will actually utilize this with what we call a virtual tool, which is just a big block built around it. Well, what that allows for is when we do a cross-section of like the temperature at end of cooling, we can cross-section through and see, there we go, cavity visibility, visibility. And do a cross-section through there and see what the part looks like, and along with the actual cutter, I'm sorry, the cooling lines, and see how they are dealing with the temperature that is being pulled from the part from the injection method through into the actual block. Heat loading, you can see how the cooling lines are hot in these areas. Okay, there's nothing in the center of it, of course. But if I turn off, let's see if I can get this one plane off here. Bring that back. We want that one. Turn off one of these other planes. There we go. So there you can kind of get an idea of what that looks like from the cooling sense. So it gives you an idea if the design is correct. Do we need to put in a bubbler or a cascade or something else to help pull more heat out of the part? Maybe there's something I've got to put in here to help pull heat out of the core down in this area. But the cooling options allow you to do that. Again, all those tools that we had available before, that we had down here, the XY plot, are also available. This gives us a little bit more information at this time because we did a full run through. So we have the flow, the pack, and then the actual cooling down here. Now, do we need almost 21 seconds full cycle in this? Maybe not, maybe so, but the tools allow us to analyze that and see what is going on. So here's clamping force in the X, clamping force in the Y, and in the Z. And then, of course, again, I can put in values that I want to probe along here and add that in. So that's at that point. That's at that point right there. And keep adding them in. Those are pressures in this case. It could be temperatures. Now that's on the part. If I add another one there, you can see temperatures. And then I can also look at the actual node temperature of the actual cooling process. So this is all filling before. This is the actual cooling process here. A couple more things before we wrap up. It's just some more visibility analysis tools that you can have here. Let me turn off a few things. Down on the bottom here is this ISO Surface Manager, which allows me to basically create kind of an array of cuts through. You want to basically like a timestamp of what it looks like. I'm doing 24 count. Gives you a quick snapshot of what the flow front looks like without having to run the flow front. And the other one that is available on the bottom here is the path line, which basically allows us to kind of trace a molecule of plastic as it enters to where it stops on the surface of the mold. So again, some more ways to visualize what is exactly going on inside of the plastic of the tool. All digital, all done before we have to make any design changes in the tool, which can get expensive. We can take care of that and handle that up front here inside of SOLIDWORKS and make the designs and test our theories out.